Suppose we have a differential equation y double prime is equal to y, and that we equate it to 0, so y double prime minus y is equal to 0, such that y is equal to the summation of n is equal to 0 up to positive infinity, cn x raised to n exists. Therefore, y prime is equal to the summation of n is equal to 1 up to positive infinity, and cn x raised to n minus 1, and y double prime is equal to n is equal to 2 up to is equal to the summation of n is equal to 2 up to positive infinity, and times n minus 1 c's of n x raised to n minus 2. Substituting this to our equation, we have summation of n is equal to 2 to positive infinity is equal to n minus 1 c's of n x raised to n minus 2 minus the summation of n is equal to 0 up to positive infinity c's of n x raised to n is equal to 0. So the main objective here is to get the recursion relation. So to get that, we need to have a same index and same index. So what we add in the bottom is what we subtract above. So for here, for n is equal to 2, we subtract 2 below and we add 2 above. So now our equation is summation of n is equal to 0 up to positive infinity, n plus 2 times n plus 1 c's of n plus 2 x raised to n minus the summation of n is equal to 0 up to positive infinity, c's of n x raised to n is equal to 0. So we're gonna combine all the similar terms and equate it to 0. So our recursion relation now is c's of n plus 2 is equal to c's of n all over n plus 2 times n plus 1. So we're gonna start from n is equal to 0. So we're gonna find the value of our coefficient. So we have, for n is equal to 0, c's of 0 plus 2 is equal to c's of 0 all over 2 times 1 is equal to c's of 2 is equal to c's of 0 over 2 factorial. Continuing, proceeding, so n is equal to 1, c's of 1 plus 2 is equal to c's of 1 all over 3 times 2. So c's of 3 is also equal to c's of 1 over 3 factorial. For n is equal to 2, c's of 2 plus 2 is equal to c's of 2 all over 4 times 3 is also equal to c's of 4 is equal to c's of 0 over 2 factorial all over 4 times 3 is equal to c's of 0 over 4 factorial. For n is equal to 3, c's of 3 plus 2 is equal to c's of 3 over 5 times 4 is also equal to c's of 5 is equal to c's of 1 over 3 factorial all over 5 times 4 is equal to c's of 1 over 5 factorial. For n is equal to 4, c's of 4 plus 2 is equal to c's of 4 over 6 times 5 is also equal to c's of 6 is equal to c's of 0 over 4 factorial all over 6 times 5 is equal to c's of 0 over 6 factorial. For n is equal to 5, we have c's of 5 plus 2 is equal to c's of 5 over 7 times 6 is also equal to c's of 7 is equal to c's of 1 all over 5 over 5 factorial all over 7 times 6. So c's of 7 is equal to c's of 1 over 7 factorial. So we have extracted the first 5 terms of our power series. So we have created a pattern for even c's of 2 times n is equal to c's of 0 over 2 times n factorial. For odd, we have c's of 2n plus 1 is equal to c's of 0 all over 2n plus 1 factorial. So substituting this value of our coefficient in the formula we have the simplified equation here. So, we have y is equal to c sub 0 multiplied by 1 plus 1 over 2 factorial x squared plus 1 over 4 factorial x raised to 4 plus 1 over 6 factorial x raised to 6 plus and so on. Plus c sub 1 multiplied by x plus 1 over 3 factorial x cubed plus 1 over 5 factorial x raised to 5 plus 1 over 7 factorial x raised to 7 plus and so on. So, notice that our series series expansion here is similarly to the Taylor series that we obtained from the hyperbolic cosine, and also here Taylor series that we obtained from hyperbolic sine. So the solution to our differential equation using power series method is y is equal to c sub 0 hyperbolic cosine x plus c sub 1 hyperbolic sine x.